Welcome to the next NCI seminar today. We have Finnegan Wilson. He's going to talk to us about flash X-ray radiographic image quality. Finnegan is a PhD candidate at the Colorado School of Mines. He has an MS in mechanical engineering and works with the Mines Explosive Research Laboratory. His primary experience is in dynamic experimental design, focusing on the mechanics of high explosive materials. At the ERL, the Explosive Research Laboratory, he operates an underground research space fielding the 3-ring flash computed tomography system. And he's working with Katie Hark and others here at the laboratory in collaboration on their PhD in getting that flash system up and running. Welcome.
Thank you so much for the introduction and for the invitation to speak today. It's about 1 year, actually to the day, since I defended my PhD proposal, getting my committee on board for this research project. So it feels a little cathartic to actually be here almost exactly a year from the day. So I'm going to talk about flash X-ray radiographic image quality for advanced applications in flash computed tomography. That's a lot of words, really, just to say we're going to talk about flash X-ray imaging, how we should maybe talk about image quality in regards to flash X-ray, and then we'll apply that to some advanced applications in flash computed tomography, specifically the 3-ring flash X-ray system, which we'll touch on a little bit here. There we go. Okay. I want to start with acknowledgements because I would not be here without all of these people, and it's really important to me to acknowledge where I've come from in order to get here. My advisor from Mines, Dr. Veronica Eliason, has been a fantastic, not only academic advisor, but also personal advisor, kind of helping me develop into the person I am today. Our co-advisor, Brian Gockel, has been a fantastic technical advisor as well, helping me attack some challenges that I didn't really expect to encounter during this program, but I've learned a lot from him so far. Project leadership here at Livermore, Catherine Hark, the PI for the 3-ring project, has taught me a lot about not only X-ray imaging, but kind of how to perform research in the national lab space. Anthony Hardy has also been really impactful, teaching me about the simulation side of things, which is something I had zero exposure to before, and he's done a really good job kind of getting me up to speed, so to speak. 2 undergrads have been really important in getting the 3-ring system installed at Mines. Ian Keefe worked with me a lot last semester, kind of in his free time as well, which was awesome. And then Tom Powell, who's actually here today and helping a lot with some novel ideas that I probably never would have come up with on my own. So I appreciate that. And then, of course, the funding streams from Livermore for at least my side of the project. Joe Tringe's DDT project, Kyle Sullivan's Mayhem LDRD, and then Dylan Klein has kind of been the liaison for our lab working with Livermore as far back as I've been working with the lab, all the way back into my undergrad degree. So Harry kind of covered this a little bit, but I just wanted to touch on this because I think it's relevant to the rest of the presentation. So I'm a PhD candidate in mechanical engineering. Again, it's been about a year since I've gained that, kind of defended my proposal and what I wanted to work on. I work at the Colorado School of Mines Explosives Research Laboratory. So this is our outdoor arena up in Idaho Springs, Colorado, shown to the right of the screen there. And our main campus is in Golden, which is just west of Denver, but kind of more mountainous. It's a little bit less urban, which I like. So I've got 3 years of experience so far with dynamic radiography and experimental design for high explosives experiments. And I guess the important context here is that my advisor, Dr. Eliason, started working at Mines to kind of pick up the Explosives Research Lab site, which had previously been run by somebody and kind of was abandoned and not taken care of for a few years there. So the knowledge transfer and sort of equipment transfer was not done effectively, mostly on the fault of the previous PI there. So we had a lot of work to do to actually get this site stood up and get our capabilities stood up. So Dr. Eliason came in with quite a bit of experience with high-speed imaging, and we wanted to not only apply that experience with high-speed imaging to some explosive systems, but also start to evaluate some of our other diagnostic techniques like our flash lighting, our laser velocimetry, and our flash X-ray, which is more what we're going to talk about today. So we start with a pretty well understood and easily available material system. This is a well perforating shape charge. It's not the traditional shape charge that you might see in the lab space. It's kind of more cheaply produced, I guess, for the oil and gas industry. Basically, it's a steel casing. We have high explosive material packed inside, and then on the output face is this copper sheet that's pressed into a cone. As that explosive material detonates, we're going to compress that copper cone out and form a stream or a jet, and that jet can penetrate through multiple inches of steel or rock specific to the oil and gas industry here. You can see it's pretty axisymmetrical, at least within their machining tolerances, and it fits in your hand. We're going to put a detonator at that top face there, this sort of black rubber part, and then we detonate this. And we wanted to take some videography of this, take some flash X-ray images, and kind of explore our space a bit. So these are some high-speed videos taken by my colleague Grace Rabinowitz. On the left, we have 5 million frames per second, and on the right, that's 10 million frames per second. In the beginning of both of these videos, we can kind of see this ring of light spread up along the edge of that copper jet, or excuse me, that copper sheet, and that's that detonation front developing inside the material. And then we're going to start to squeeze that copper out with the expansion of the detonation products. It's worth noting that while we can see the arrival of that sort of ring of light, giving us an idea of simultaneity in this object, we can't really see much after that jet is formed. Not only do we have too much debris and too much light produced, but if our camera was tuned to kind of get past this overexposure in the light, we wouldn't be able to see that ring. So clearly we need another tool to actually understand the physics here if we're interested in the jet. That's where flash radiography comes in. Here we see that same well-perforating shape charge. Microseconds into its detonation process, there's a little bit of debris at the top of that left image from the detonator going off, and we can see that copper jet streaming down towards the target that we were shooting at here. You can also kind of make out this arrowhead shape in the center of that steel casing, and that's the remnant of that copper material being squeezed out the jet. Now, a handful of microseconds later, the case completely fractures and the jet kind of peters out. I'll point out here that this is an axisymmetrical object, within their machining tolerances, but it's exhibiting a little bit of asymmetrical behavior, which is worth noting because we are trying to capture this using two-dimensional imaging, which is not necessarily effective to capture all of the details going on. Not super important for this specific shape charge, but we should keep that in mind as we move forward. It's a little bit of foreshadowing. So if you're unfamiliar with flash X-ray radiography, it's another flavor of dynamic radiography. You may be more familiar with radiography done at like a beamline or a linear accelerator, where we have nice brief pulses of monochromatic X-ray photons for very short amounts of time emitted in a nice clean way. They typically don't want explosives in these kind of facilities, especially at the yields that we're working with, because these facilities are very expensive and can be used for tons of other types of imaging. So instead, to get our pulses of X-ray from a flash X-ray system, we're using a Mark surge generator, which is a layout of capacitors. They're charged in parallel, in our case, to 35,000 volts, and discharged through a series of spark gaps, effectively adding up all of their energy and resulting, in our case, in a pulse of 450,000 volts at about 6,500 amps. This is going to give us a very short, about 20 nanosecond pulse of X-ray photon intensity, which we can use to take images of these highly dynamic events. I'm showing an arrangement of the cathode and anode to the right there. It's effectively a washer with a sharp edge to kind of focus the stream of electrons onto that anode, which is kind of shaped like a pencil tip. That anode is made of a material like tungsten, which is going to rapidly decelerate those electrons, and that energy from the kinetic energy of the electrons, is going to be transferred into heat and into X-ray photon production. And this gives us a really noisy and polychromatic X-ray spectra called bremsstrahlung. I have what's effectively a system performance plot in a really qualitative sense down on the lower left, showing the production of voltage, which leads to the discharge of current, the dotted line. And in that very initial phase where our voltage is sinking down and our current is growing, we actually see the very brief production of the dark line, S, which is photon intensity in this case. So again, we're getting fractions of a microsecond here, 20 nanoseconds. Flash has been around for decades, and it has a lot of use to take qualitative images to understand what's going on in the case of our shape charge, but it's also been used historically as a quantitative tool if you use it effectively. This paper by Neil talks about a number of different ways to do this, and one of the ways he shows is taking a group of explosive material, think like a brick of explosive material, in intimate contact with a thin sheet, and we're shock loading that sheet. And what we're going to see is the production of ejecta, or little particles being thrown off the back of that sheet due to the shock interaction. Here he's calling it fluff, which is a little hand-wavy, but it works. So what they're going to do here is, instead of just taking an image of this fluff that's produced and qualitatively showing what's going on, he's going to take a microdensitometer, which is basically a slit that they're using to analyze the film density along this interface, going from the shocked material into the fluff and then into the air beyond it. And we can see that there's clearly a change in the film density responsible, or that is caused by the production of that fluff. That gives you kind of, again, a qualitative image, but inside this image, Neil is including a little step wedge. And that step wedge has known attenuation characteristics, and they then know the effect of those attenuation characteristics on the film density. And thus they're able to estimate the mass density of this produced fluff or ejecta simply by calibrating to a known object with known behavior. So we use flash imaging a lot in a qualitative sense at Mines. All of these pictures are shown from our explosives research lab at Mines. This is a cartoon of our static geometry where we have about a 2-inch diameter tube of C4, and we're shock loading a little metallic sample in orange down there at the bottom that's held in a annulus of PMMA. So we can see we can see the different material holder, the actual material slug, and the tube of explosive in the static image in the middle. And then to the right, we can see that our detonation front, which is moving at over 8 kilometers per second, or 8 millimeters every microsecond, about 36 microseconds into the experiment. We're able to get a pretty clear and sharp image of that detonation front, at least on my screen. I'm not sure how it's coming through on the projector there. But we can actually identify not only the curvature of that detonation front, but its location in space from our very short pulse of X-rays here. Another use case that we have for flash X-ray at our lab is to look at material deformation and the production of a projectile and its flight through its time of life, effectively. So this is the same experimental design. We've just added little pins in there to measure the velocity of detonation. So there's a static image, and then shortly after the detonation front passes through, we see mass deformation not only of the plastic housing, but also we've effectively created a little trapezoid cross-section from our previously square cross-section of that metal sample. Now, tens of microseconds later, we see the sample deformed and in flight. This actually gives my colleague Grace a good window for understanding where we can actually capture the deformation of this sample, and when she moves to her actual sample of interest instead of just this aluminum slug, we expect to see fracture occur within this window, which we'll then be able to pick up with the flash X-ray system. I kind of alluded to this earlier. I've shown you mostly symmetrical setups so far, but we're also very interested in asymmetrical processes, which are certainly inherent to explosive mechanics. This specifically is from Joe Tringe's DDT project, where we're looking at deflagration, so burning, to detonation, so like full high order, the reaction front is moving supersonically within the material, and we're interested in how that transition occurs. So at the bottom, I have a cartoon showing what this experimental setup looks like, where we have some thermite or another pyrophoric material that's going to initiate a burning material or a burning reaction inside that high explosive, which is the orange column. What we're going to see is this dark area on the top radiograph there. That's the burned material and burn front moving to the right. It's going to produce this plug of condensed material ahead of it. And as that material continues to burn and pushes that plug, we're going to see this material condensing. We're going to see pressure release, and eventually, specifically down at the second or third image, we see an interaction of that burn front with the actual plug of condensed material. So what's going to happen in there is a transition to detonation, yet we don't fully understand that mechanism in the type 1 DDT process. You can also see that this is a symmetrical object that is exhibiting an asymmetrical behavior, and because we're only capturing two-dimensional images of it, we're not effectively describing the volumetric distribution of density in here. And so there is some information that's lost in the way that we're capturing this data. This necessitates a way to actually generate or capture three-dimensional data or three-dimensional images of this particular problem. That is a good introduction into the three-ring flash X-ray system. Here is a spherical distribution of 15 flash X-ray sources and detectors, all operating at the 450 kilovolt peak max energy, and it's designed for about 1.5 pounds of TNT net equivalent weight, which is a considerable amount of explosives. Here we have a 20 nanosecond pulse duration. We're using the same type of flash X-ray system we've already talked about, so we've maintained that short pulse duration, and we've got about a 200 by 200 by 200 millimeter viewable area. This is going to utilize few view reconstruction algorithms to perform this tomographic reconstruction of our events from only 5 images. Effectively, that allows us to create a 3-frame, 3-dimensional movie of these dynamic events, allowing us to watch the volumetric evolution of these density fields in time. So, like I've said, we're going to use about 5 images, so this creates a very underdetermined problem, meaning we can't use like a traditional analytic filtered back projection reconstruction to perform this reconstruction. Instead, they're using an iterative solving process called the few view reconstruction algorithm. I'm probably butchering that actual terminology. So here is an example taken on what is effectively the predecessor to the 3-ring system. They're looking here at a steel-jacketed bullet penetrating through an aluminum plate. And we can actually see these are 3-dimensional reconstructions done. There's 3 of them in the row down there, giving us a time sequence not only of the penetration, but also of the production of some of this spall and fragments off to the side there. So 3-ring was designed and built here at Livermore, and a few static images were taken, but dynamic fielding has not yet occurred. And so in order to have a permanent location for 3-ring, so it doesn't have to be, it can be permanently set up to allow for debugging and actual dynamic fielding. We've created a space underground in the Edgar experimental mine at the Colorado School of Mines. Our group actually participated in the design of the blast pattern to remove rock from this underground space, which is called a drift. In our case, this is the sunburst drift. We went in and removed the blast rubble, tied in rebar, poured concrete, and installed a grounding system and everything. The electrical system got installed, and then the ceiling was shotcreted to kind of help hold out water and keep any smaller rocks from falling during blast operations. The 3-ring team came out to visit us. I believe that was back in 2023. 3-ring was then shipped in the summer of 2024. There I am standing next to the big 4 Connex containers. Those are all 20 feet long. That 3-ring was shipped in, and there's 3-ring sitting in its tall Connex container there. So the dynamic fielding is coming very soon. We've spent the last 6 months working to actually install the system underground, get it all wired up and plumbed in, kind of work out some of the kinks in controlling the electrical system. You can see all the control cabinets are set up in there, so now we have all of our high voltage control, all of our trigger generators, all of our gas control, everything not only installed but also proved out and tested. At this point, what we have left to do is perform our commissioning experiments, where we actually measure resolution, and we'll get into that a little bit later. So now that we have an idea of where we're going with all of this information, not only the sort of past use cases of flash X-ray, but also what we hope to do with it in the future with the 3-ring system, I kind of want to take a step back to how I learned about flash. So again, Dr. Eliason was fairly new to the explosives space and new to the explosives research laboratory. There was a 2-channel, 450 kilovolt flash X-ray system sitting on our site, but it was kind of buried in the dirt. A lot of the parts had either gone missing or been moved to different connexes and storage locations. And so we had someone from L3, the company that manufactures this specific pulsar system, come out and show us how to actually put together the system. Although we didn't get it firing with him, he did a fairly good job getting it set up with us. But then I asked the question, as a new PhD student interested in understanding the system I'm working with, what settings should I use to take a good image? And he said, maybe 28 kV, 68 psi. And I said, what motivates those settings? And he said, well, I mean, they work. You can get an image. That wasn't a particularly satisfying answer. Again, as somebody that was a little more interested in having a quantified metric of like, why are we doing this? Can we do better? I asked the same question about the detector that we have. Well, he points to the one that was sitting on the shelf there and said, well, you have that one, so you should use it. Again, not a particularly satisfying answer, but it certainly works. L3's user manual, which this guy helped walk us through to get the system set up, is fairly helpful for system use and maintenance, but it really doesn't talk about setting up a good quality image or even what a quality image is. So that begs the question, what can we find in literature that actually talks about image quality and how to apply that to radiography? This is a great paper released by Heenan back in 2020, talking about analytically calculating the transmission, so the amount of X-ray radiation to get through your object, required for your highest possible contrast to noise ratio in an ideal detector system. They determine this to be about 13.53%. So then they go in with their known material, which I believe is a battery cathode for a lithium ion cell, and they say, okay, what thickness of this material is going to give us this transmission, and thus our highest possible contrast to noise ratio, at all of our different monochromatic beam energies that we're exploring. And they produce this really nice spiral plot, which again is very useful if you're studying this battery material with this type of X-ray system. We are trying to apply this to a much more polychromatic system, specifically with flash X-ray, and we're not really interested in this battery cathode material. We're interested in these detonation experiments where we have unreacted material, we have our shock front or our detonation front moving inside of that material, and we have expansion products out the back, maybe interactions with walls, interactions with metal samples. It's a lot more complicated than just trying to resolve this specific material against the air. But this is a really good place to start. We know that there is an optimal transmission that gives you a really good image quality metric like contrast to noise ratio. We can address the other question as well. How do different detectors compare? This paper by Ornhead back in 2003, they're trying to answer that same question, looking at computed radiography or storage phosphor imaging plates versus traditional film and scintillator or intensifier screen. What they're going to do here is take multiple flash images on a flash X-ray system and compare the ability to form a high-fidelity digital image. You can see what they've demonstrated here is the same object, so step wedges, cylinders inside of cups. They've got a dosimeter here, which is moved between the two shots, but it's the same dosimeter. There's very clearly a difference in performance here. And depending on what we're looking for, we have a different optimal detector system to actually use here. So this is promising. This tells us that we can change our image quality by using a different type of detector, and maybe there is one that is best or one that is best for a specific application. So now that we've kind of looked at, there is an optimal transmission, right? There is a difference due to the detector, right? These are things we do need to consider moving forward. We want to ask the question, what image quality metrics are important to us? I've written metrics of interest for in situ performance. And what I'm trying to say here is I'm not just interested in, again, looking at an object in its difference to air around it. We're interested in seeing compound objects or material interfaces that are moving very quickly. And they're often very small, right? We're interested in these small curvatures inside of a detonation front. So we can kind of talk about these different common metrics of interest that we see specifically in radiography. We can look at a raw intensity measurement. So this is just the digital pixel values captured by either your detector or your scanner once you've scanned in your detector. And you can see this is a little dark. This comes from our flash X-ray system of the same experiment I've showed you so far on the Flex GP computed radiography plate system. It's a little hard to make out anything because in terms of, I guess, the maximum digital value here, we're a little low. So we can normalize this by the background or by the air, creating what's called a transmission image. Well, now we can see a lot better what we're trying to look for. We can see our different material interfaces, and we can even see our detonation front a lot better. I'll point out here that you can tell that there's speckling around the air. This is a transmission image, so you might expect the air or the beam that is transmitting through not the object, that's going through the air would have a transmission of 1. And it's very close to 1, but because it's such a noisy process, we do see this variation. So noise is very important to our metrics that we're looking at. You might ask about a signal to noise ratio. And the question becomes, well, what is your signal? Is it the transmission value of the specific region that you're looking at? In this case, are we looking at the transmission of that little metal block that's in there? I've got a line out plotted here. So along the red line in the image, I've plotted out the raw pixel values in transmission space along this slightly wider plot. And you can see that there's kind of a uniform region of transmission where that object is. So that could be our signal, but Again, we're interested in seeing the change in transmission between, for example, either the air and the metal, or the unreacted explosive material and the detonation front a little further to the right. That becomes a measurement of contrast, or a contrast to noise ratio. We can also evaluate something like a step response. So you can see that we're looking at air right next to basically a rectangular object. So we should expect a abrupt change in our transmission, but there's very clearly a physical thickness to that edge crossing, and that has to do with our spatial frequency response and the blur introduced by our system. So we can look at a step response metric, or more commonly, we can look at something like a modulation transfer function or a contrast transfer function. So our ability to resolve a difference in contrast or modulation dependent on spatial frequency. Now that we have an idea of maybe what types of imaging metrics we want to look at, we've decided contrast to noise ratio is of interest to us and a contrast transfer function. We can move forward looking at input parameters for a flash system. I've broken this down into a couple different ways to talk about image metrics or image parameters, excuse me. Here we're looking at differences in the pulsar. So this is the capacitor bank. This will affect your charge voltage, which is linearly related to your output voltage. Or we can look at the output cable length, which will change the way that current is delivered to our tube head, which is where the x-rays are produced. We can talk about differences in our detector system, where we're looking at different types of detectors. For example, computed radiography imaging plates, film with a scintillator screen. We can also look at a flat panel digital detector, or even a scintillator with a camera filming that scintillator from behind. The shielding is very important. Again, we're doing explosives experiments here. And if we don't have proper shielding of our detectors, we're going to destroy them and either not be able to use them again, or worst case, not be able to recover the data from them. We also want to talk about the concept of scanning or digitizing. Specifically with film and computed radiography plates, we are producing a physical image on a physical substrate, and that needs to be scanned or digitized in order to analyze it comparably with our other types of digital images. Lastly, we can talk about the flash X-ray source, or the tube head. So this is going to be factors like your anode size, your cathode shape, and the way that it's distributing that flow of electrons onto the anode. Your anode material is very important. This can change your overall Bremsstrahlung spectra. The anode wear is also going to prove to be very important, which we've seen empirically in some of our experiments that we've run so far. So how many shots are on this anode? The anode physically degrades each shot. Is this happening repeatably? Is this happening in a way that we can measure and predict? And lastly, the concept of source filtering. We can perform beam hardening, where we're shifting our overall output spectra towards higher energies by knocking off some of the lower energy components of that spectra. But in doing so, we're actually going to take a significant hit in our overall photon flux, which proves to be very impactful, particularly with film, as we'll see moving forward. So there's a balance here that needs to be struck. Along with 3-ring, Livermore built the flash X-ray testbed. This holds one of the sources from 3-ring, this right-angle Scandi flash tube, about 116 centimeters from our detector face. And we can change out the detector either that's on the face of that or behind the protection there. This allows us to repeatably and much easier than on the 3-ring system iterate through different system parameters, different objects, different types of detectors to explore our image quality in experimental space. Here we can see a rendering of the X-ray source with the collimation, which kind of helps cut down on any of the X-ray photons that would not impinge on the detector surface, helping getting rid of crosstalk in the larger 3-ring system, meaning source number 1 impacting detector number 7, for example. We've primarily looked at 2 different objects throughout these experimental campaigns. The first is an aluminum step wedge, where we have different distinct regions of transmission. It's the same material with the same linear attenuation coefficient, but these different amounts of material are going to attenuate that beam differently, resulting, for example, in the transmission image to the right, where we see these distinct step regions, and here we're actually taking that step region in orange and comparing that with the region in blue. We're keeping those region sizes the same, and this is how we're going to calculate contrast to noise ratios between those two in our results that we'll present. The second object is a line pair gauge. So here we have 2 lines and a gap between them, all of the same thickness and diameter. And then the next line pair below it is going to be closer together, resulting in a higher spatial frequency, and so on and so forth. A common transmission response to this line pair gauge is shown on the right, where we can actually see that we're losing not only the ability to resolve the contrast between those two lines, that difference in peaks is getting smaller and smaller, but we also lose the ability to resolve the fact that those are two individual lines at a certain point, and they basically blur together into one gray blob. And that's what we are considering our maximum spatial frequency that we can resolve in this system. In order to keep all the evaluation fair, we want to treat all the images the same. So our film and our computed radiography images, which we've looked at, are going to be created into transmission images. We're going to normalize the image with the object by an image without the object. So each pixel value is from 0 to 1, how much of the original beam made it through the object. With the digital radiography images, we're treating these fairly similarly, but we're accounting for something called the dark image. So these are actually physical pixels on the detector that are driven by a current, and that can produce like electrical differences, leading to a difference in pixel response. By subtracting the dark image here, so an image taken without illumination, we can kind of correct for that spurious effect, or any pixels that are damaged and just producing like a value of 1 when there's no X-ray illumination. The transmission that we're using for our metrics here is the average pixel value inside these regions of interest, which is the step face, or that same size in the air. And the noise that we're using to quantify here is the standard deviation of those transmission values within the region of interest. I'll point out that for the different types of detectors we've looked at, film, computed radiography, and digital radiography, those image sizes come out with different numbers of pixels, and thus the regions of interest, the step face, are going to be different sizes, but we're still keeping that same, rough region highlighting the actual step face. We can see down there, down at the bottom of the screen, our contrast calculations with our error bounds. In this case, T naught refers to the transmission in the air, and T subscript S refers to the transmission in the solid. Similarly, our contrast to noise calculations with error bounds, the little delta symbol there is referring to noise with the same subscripts. And then NROI at the far right is the number of pixels inside our region of interest. So now we can actually look at some of the data comparison that we've done so far. This was the first set of experiments that we ran. We captured images on different detectors with identical input parameters. So this is at 450 kilovolts peak and about 2.93 millimeters of copper shielding. It's worth noting here that the digital detector is kept inside blast shielding. It's a lot more fragile than the other types of detectors, but that's how it's going to be fielded in 3-ring, so we're just equating that as the HPX performance. Here we're comparing the HPX DR3543, which is the type of detector we plan to use in the 3-ring system, and we're comparing that with multiple computed radiography plates. In this case, the Flex XL Blue, Flex GP, and Flex HR, which are commonly used between the NDE groups and HEAF, the High Explosive Application Facility here at Livermore. So the first result on the left there is looking at contrast to noise ratio at all of the different steps of aluminum. We can see that the digital detector has the highest contrast to noise ratio at all the steps. In the middle there, we see the Flex GP panel, so that's the one that we have on our site. Turns out the guy was right, that is a pretty good panel to use, so good job, Peter. And then the lowest performing panels in terms of contrast to noise ratio actually prove to have the highest resolvable spatial frequency on the plot on the right, or at least the Flex HR panel does. We see sort of a trade-off going on here. Our digital detector has the lowest performing spatial frequency results on the right, and that's partly tied to the fact that the physical pixels on this digital detector are larger. They're about 139 micron in diameter compared to about 65 micron for the computed radiography panel, so they cannot resolve the same amount of line pairs. When we went and did the second version of this study to add another type of detector to this data set, we were looking here at film. Specifically Carestream's HS800 film using LANX medium F intensifier screens. So again, this is the same plots, but we've added 3 different cases of film with different amounts of filtering. When we originally took the film images, we used the same 2.93 millimeters of copper filtering, but what we saw is that that didn't produce enough contrast to actually resolve some of the steps. So instead, we reduced that amount of filtering, shown here as 0 millimeters, 0.75 millimeters, and 2.13 millimeters that we've explored. And there's a pretty clear impact on the contrast to noise ratio here. So 0 millimeters of filtering gives us almost double the contrast to noise ratio that we saw with the digital detector. Even adding 0.75 millimeters of copper puts us on par with that digital detector. and then adding 2.13, still less than the original other types of detectors, we are back down at the lowest performing computer radiography plates. We see that we don't have a super significant impact on our spatial frequency results using this different amount of filtering, which we'll talk about in more detail in a second. So I alluded to the idea that we have all these different parameters that we can tune inside of this space, right? Charge voltage, filtering, and maybe the assembly of that film pack. So what I'm trying to do here is show you all of the different results in contrast to noise ratios that we captured by tuning these parameters. So the top two plots here are looking at our lower energy, which is 386 kilovolt peak. The bottom two plots are looking at our higher energy, 450 kVp. The two plots on the left are captured using a single Lanix intensifier screen, and the two plots on the right are looking at double Lanix intensifier screens in our film pack. And then within each plot, we're looking at the contrast to noise ratio versus the thickness of aluminum, as we've done before, and we're comparing the amounts of copper used in filtering. Some big results immediately. Adding filtering for film strictly decreases our contrast to noise ratio. We also see that adding a second Lanix screen results in higher contrast to noise ratios, but it's hard to tell if that's really apparent at every single step, so we need to do some sensitivity analysis. We can also see that in the top right and lower left-hand plots, we've captured some repeat data points with the same exact input parameters to try and measure run-to-run variability. I've alluded to the fact that flash is a bit noisy, and so we want to quantify this run-to-run variability in order to do a sensitivity analysis. This is the same distribution of results, but instead of contrast to noise ratio, we're looking at the spatial frequency response versus the contrast of those line pairs. The main takeaway here is that the addition of a second Lanix screen or a second intensifier scintillator screen introduces more blur into our system. So the two plots on the left with a single Lanix screen have a higher maximum spatial frequency resolved. The contrast values in here are hard to interpret, and I will touch on that a little bit later because I think this is tied back to the way we went about evaluating this data. But the real thing that we should focus on right now is the spatial frequency and the highest spatial frequency that we can resolve for each configuration. In order to perform this sort of sensitivity analysis, which I'm using kind of loosely there, we want to isolate the effect, for example, of source filtering. So again, same distribution of parameters here, but inside each plot, instead of looking at the contrast to noise ratio, we're looking at the difference in contrast to noise ratio caused by turning our filtering dial by one level, going from 0 to 0.75 millimeters in blue, and the plots with green going from 0.75 to 2.13 millimeters of filtering. And we're comparing that with this black dotted line at the bottom there, and that is actually calculated with our run-to-run variability from our previous plots there. What we're doing here is basically we're able to tell that by adding our first level of filtering, we have a significant change in our contrast to noise ratio at every step. By adding more filtering, so going from 0.75 to 2.13, there isn't always a significant change, particularly at those lower thicknesses of aluminum where we have higher transmission. That is less sensitive to a change in additional filtering. We can also kind of broadly pull from here that where we had higher contrast to noise ratios, more thickness of aluminum, we see a more significant or higher change in our contrast to noise ratio simply by changing the filtering. We can perform a similar analysis by isolating the effects of the intensifier screen count. So on the left, we're looking at our 386 kilovolt peak data, and we can see that there is a difference in sensitivity those different curves. Blue is looking at 0 millimeters, comparing 2 Lanix screens to 1 Lanix screen, and green here is looking at 0.75 millimeters, comparing 2 Lanix screens to 1 Lanix screen. We can see that the different filtering levels have different sensitivities to the addition of a second Lanix screen, and we are not always seeing a significant change, particularly on the right at 450 kilovolts peak. Our highest filtering case doesn't see a significant change in contrast to noise ratio till our 38 millimeter aluminum step. What's happening here, at least what I believe is happening here, is that if we're not getting enough photons through our filtering, well, we're going to have trouble resolving a high contrast to noise ratio through the object. And if we're not getting enough photons even through that object, then we're not going to see a significant change by the intensifiers, which rely on X-ray photons in order to produce photons in the visible spectrum in order for us to actually capture an image on the film. So again, film has proven to be very, very sensitive to your photon flux, and we really need to be careful of that as we tune a film system. Last step here, performing the isolating effects of charge voltage or peak voltage. So I've got on the far right there a relation between our input charge, 35 to 30 kV, and the Marx generator peak output, either 450 all the way down to 386 kilovolts peak. The main result, or the main takeaway from this plot, is that we did not see a significant change in contrast to noise ratio simply by changing or isolating the change from the charge voltage. I mentioned this earlier, we're interested in studying the scanner and the scanning effects. So we explored a bunch of different parameters using a single film image here. This is with the VIDAR NDT Pro film digitizer. So with optical density range, we explored from 1.0 up to 4.7. And I'm only plotting 4.0 through 4.7 where we don't see a significant change. Under 4.0, we couldn't actually resolve some of the thinner steps of aluminum. They just were washed out in white. Maybe that's something that should have been included on this plot, but here we can see that within this range between 4.0 and 4.7, it doesn't really matter what optical density you're measuring. That plot to the top right is a little misleading because the contrast to noise ratio scale is much higher than its neighbors, and we're going to touch on that in the next slide, but you can see that pixel size had a very significant effect on our overall contrast to noise ratio. Digital bit depth between 12-bit and 8-bit did not really have a significant effect on contrast to noise ratio. And then for our scanning mode, whether that's quality, speed, or standard, only really matters at those thicker steps of aluminum where you have lower transmission. So if you want good quality data, just keep your scanner in quality mode. Speaking specifically about that top right plot, we can look at the trade-off in metrics. So here, again, this is the contrast to noise ratio versus thickness, while changing the pixel size from 50 to 500 micron. And then we're going to compare that on the right with the spatial frequency response. And we can see that even though we've effectively artificially increased our contrast to noise ratio up to over 150 by increasing our pixel size, we've had such a reduction in the maximum spatial frequency that we can attain, below 1 line pair per millimeter, that this is not really a viable path forward for increasing your contrast to noise ratio. Perhaps if you knew the spatial frequency you were interested in your image, you could tune like this. I wouldn't recommend it though. The image is kind of looking very fuzzy, and I was surprised that we even got above 0.5 line pairs per millimeter with some of those higher pixel sizes. So I alluded to this before. I want to address the contrast transfer function results. So this is our contrast that we resolve at each spatial frequency. You might be able to pick out in some of those earlier plots that there's a lot of variation and it doesn't seem to follow a specific pattern. And what I think is happening here is this is an artifact of how we went about extracting the contrast values at each spatial frequency. So I wrote a piece of software that it would handle the images, it would actually handle creation of the transmission images and the contrast analysis. And then you would tell it a little rectangle or swath to actually look at where you have your line pair response. And then it's going to average out along the short direction, giving you this line in transmission space. And then you can either use an automatic or a manual peak detection and kind of pick out, this is the first line pair, this is the second line pair. Please calculate the contrast at that location. And it's going to calculate the contrast between those lower values on that lower right plot, which are at the center of our lines, and then compare that with the gap between them, the error, and that's the peak in that plot. We ran this several different times, tens of times, even with different lab members. Everyone's selecting a slightly different size region for this swath out at the first step. And what we found is that we are very, very sensitive to that. So as the spatial frequency increases, even above 2 line pairs per millimeter, we start to see a massive range as a percentage of the mean value from this analysis. This is kind of telling us that the contrast value that we extract at all these spatial frequencies, particularly above 2 line pairs per millimeter, maybe are not the most reliable metrics to actually measure here. But interestingly, when running this experiment multiple different times on the same image, we were able to resolve the same highest spatial frequency, just with varying contrast amounts. I think what this is telling us is that we have a good way to look at the highest spatial frequency that we resolved, just maybe not the best way to look at the contrast at that specific spatial frequency. I have some thoughts on why this is, but it might be a little out of scope for this. In terms of continuing the work in this experimental space, we are continuing to work with 3-ring, but the flash testbed is actually being sent to mines currently, and we plan to do a whole bunch of other studies in this similar space, looking at image quality, looking at contrast to noise ratio, and spatial frequency response, while exploring these different, maybe these different impacts on our source and detectors. Particularly anode degradation sounds like it's particularly interesting to people at the lab. I'm particularly interested in it. This is an image that Katie captured of a pristine 1mm anode next to an anode that's at the end of its useful lifetime. And we can see we've lost a considerable amount of mass and deformed the tip. We've even changed that taper angle. And if you zoom in there, you can actually see that we have like blobs of this tungsten material on there. So we are doing significant damage to this tungsten anode even after 30 shots here. We want to know if this is repeatable. We want to see the effect on the output spectra and the output intensity. We want to see if the spot size wanders or changes its physical size, which would introduce more blur into the system. We really want to map out this space because everyone uses these flash anodes who uses these flash X-ray systems. And if we have a good idea of how they age, and if they age repeatably, we can either correct for this after the fact or identify when an anode needs to be changed in order to not compromise image data during an experiment. The results I've shown here highlight the sensitivity of the Carestream's HS800 film to your overall photon flux. What we've seen, though, is that we have a lot more adjustability looking at the digital detector, the HPX, or the computed radiography plates, as they required filtering to not overexpose these images. This kind of tells us that they're not going to be quite as linearly sensitive to the amount of filtering that specifically the film was. So this is hopefully going to be a space where we're going to see some better adjustability and not just a sharp reduction in contrast to noise ratio. I'm particularly interested in the concept of taking a line-out metric, so just along a single line in space, and looking at those pixel values versus a swath-out metric, so averaging along a short dimension in a rectangle. And the reason I'm interested in this is, as we've seen with some of our line-out data, right, there is a very specific change, like there's noise present there, and if we take a swath out, we kind of drown out a little bit of that noise. But what's interesting is that, because we're looking at detonation front, which can have curvature, you can see curvature in this top left image, we don't know, how that curvature is going to affect the way we calculate the swath out metric. So we're going to basically create artificial blur if we average across a zone or a swath instead of looking at the line. I want to know how we can compare these metrics to each other. Can we compare them like apples to apples, or is it more of an apples to oranges situation? And then what is more impactful for us as we move forward? And then I want to highlight, this is a GIF of about 31 flash images taken from this specific anode's lifetime that Katie captured on the flash testbed here. So you can see a very clear degradation in the output intensity. And there's even some apparent spot wander in here where you see this light almost look like it's shifting around. So there's very clearly some interesting physics going on here that we want to capture in experimental space to help map to simulation space. I was asked at a conference recently, what is the minimum contrast to noise ratio do you actually need to resolve a detonation front? And I don't have an answer for that. The contrast to noise ratio that we've looked at so far is using these kind of averaged swath out metrics. And the way that we've looked at our detonation fronts is typically using a line out. So I don't know if that's something that we can apply as directly or if we need to change the way we calculate this metric. But you can see in this image, this set to the left, where we actually can see the detonation front where the green cross is. We can also see in the live line out where the green cross is, there is a change. It's very subtle, but there is a change in your live line out there. But in a similar experiment, so same material, same thickness, but different casing to the right, we actually can't see that detonation front in the radiograph. We can tell where it is based on the expansion behavior at the edges of this sample, but even in the line out space, we cannot identify where that detonation front is. So very clearly, like the subtlety in that first image is apparent, right? It's going to be a small contrast to noise ratio that we need to actually resolve this, but I'm not sure what that value is, and I'd like to have a good answer for that as I write my dissertation. Moving forward with 3-ring, we want to capture all of this information in experimental space so that we can create a high-fidelity simulation platform with all the parameters of the flash system and the detectors mapped out to their image quality effects. This is something really driven hard by Katie Hark, who's the PI for the project. We want to be able to simulate the dynamics of the experiments with, for example, a hydrocode like AL3D or Marble, and then take the output of that hydrocode and simulate radiographs taken with 3-ring using something like Hades. We can then optimize the image with the known parameters to tune if we have a good understanding and a really high fidelity simulation platform, meaning we only have to run one experiment with those optimized parameters instead of exploring this on a complex experimental platform like 3-ring. And lastly, moving forward with the 3-ring system, now that we're all set up, what we have to do is evaluate our spatial resolution using relevant objects to what we will be imaging in a dynamic setup, and our temporal resolution. For example, imaging Teflon spheres close together at sizes that are relevant to explosive articles of interest like Prill, and then how simultaneous are our simultaneous images. If we say we're taking 5 images at the same time, we want to have an idea of the error between, or the time error between those images, which will help us kind of limit the difference. I guess it will help us design our timing system so that we can limit that drift between images, because more mistiming will introduce more error into the reconstruction process, and we want to avoid that before we even go down the path of reconstruction here. So in summary, we've talked about flash X-ray as a tool, flash X-ray image quality, and how we should talk about image quality with respect to flash X-ray. We've talked a little bit about some ideas behind tuning X-ray image quality. We've shown you our experimental results from the flash testbed, and we've introduced 3-ring, sort of a summary of it, and talked about the path forward at Mines here. And then we've touched on some future work which is relevant to the flash X-ray image quality that we hope to apply both at Mines and here at Livermore. And with that, I'd like to thank you for your time and attention and open the floor for any questions.
Can you guys hear me?
We have somebody in the room first. Can you hear them? We'll go to you, Joseph, next. Let's see. Can you hear Richie's question? Probably not. Joseph?
Here, do you want to?
You can probably repeat it.
Okay.
So ask your question, and then we'll have Finnegan repeat it. So I was wondering for your flash test,
Mm-hmm.
swapping out, say, detectors or sources, what sort of acquisition software do you use? Are you just using what comes with the detector to make an acquisition?
Yeah, so far the question was, as we explore on the flash testbed, what type of acquisition software are we using as we change our different detectors? So typically what we're doing here is using the off-the-shelf acquisition software. So whether it's the software that drives the scanner for the digitizer, either for film or for computed radiography, those are different softwares, but they're what's used in that space, whether it's at our lab or at HEAF or in the NDE group. So instead of writing our own custom software there, we are just taking the image output from those scanners. But the scanner results that we looked at, we were exploring the differences within that film scanner software, if that makes sense. We can talk about that maybe offline, but we are exploring a different way to handle the software behind the digital detectors, since just one of them is fairly easy to drive, but with 15 of them on one system, it's a little complicated to drive all of those, and so we're actually exploring that at Mines, how to do that more effectively.
Joseph, you want to ask your question?
Okay, can you hear me then?
Yes.
So you showed before that the X-ray intensity changes with each shot, and some of the measurements were done at different time at different shots. So when you're comparing one measurement with a particular detector or a particular filter, it's a different shot, so therefore you may have different intensity. So it would be difficult to compare. So if that's the case, maybe some of the future studies can be done with a stationary or regular source, standard source that we have, that is more or less that you can compare more or less with these flash sources, and then you will have a more consistent intensity. Is that viable or doable?
I mean, I think that that's a valid space to explore, because it's really important to have this kind of parameter-based understanding in all of our different types of imaging techniques. We've mainly been applying this work to Flash because we're interested in how we can map out this space experimentally and in simulation world to the 3-ring Flash X-ray system, which is kind of stuck using the 450 kilovolt peak Flash system. So I think you're right that that's something that can be applied to a ton of different types of imaging technology, but we've really been staying in the Flash space because that's what we're going to apply this work to in the end.
So along those lines, did you normalize, if the intensity was changing, would you normalize for the variance in the intensity before you did your calculation?
So by doing this flat field correction, that's what we're trying to do by normalizing for that change using the air in the image.
So when you talk about the flat field, right,
Yeah.
INOT, are you talking about, so you acquire it before you do it with the object, but then you also can then, you use like a postage stamp and say, okay, this shot is half the value, so you'd have to increase that value to be consistent with the INOT value, right?
Right. And so at this point, we've done like you take an image without your object, and then right after that, you would take your image with your object. And so that is absolutely something that's baked into the variability in our results, specifically in transmission space. The way that we handle our images at mines typically is capturing a postage stamp, though. Okay. And so that has a bit of spatial effects because we have a cone beam, and so you're not always capturing what I would call like a great region of intensity. But that's something I've got in mind, and I would like to formally explore, whether it's with this data set on the Flash X-ray testbed or what we capture in the future. Because you're right, that absolutely produces different amounts of results.
Other questions in the audience? Questions online? Unmute and ask your question.
Yeah.
Some we'll take offline. One of the questions I had is, nice study, thank you. There was a lot to digest, and you went through it pretty quickly. And so given the research you did, how do you optimize your results for a particular application? So now you have an application, maybe, and the question is the requirements defined? So now you know the requirements, and so do you have a methodology now, or have you ever thought of methodology to say, okay, here's how I'm going to optimize KV, MA, if you can do that, the detector I'm going to use, the scintillator, do I do 2 or 1, and those kinds of things?
So now that we have the space kind of mapped out and we have a path forward to map out additional parts of the space, what we would be able to do is take kind of what I said at the end here, where we can take, for example, a hydrocode result of a time step in a dynamic experiment, and using work performed by Anthony Hardy and others at NDE, we can actually simulate that in high fidelity using what we know about our specific spectra and our specific detector energy response. Now that we've mapped out kind of the effect of these different parameter tweaks, we can then tune that, looking for example, a 13.5% transmission or a higher contrast. I guess if you're looking at like a metal interface, a 13.5% transmission of that metal with respect to air. So we have kind of an idea of what would be a good contrast with air. I don't necessarily have an answer of what would be the optimal transmission compared to like a detonation front versus unreacted explosive, but I'm interested in following Heenan's process of analytically calculating that with sort of known attenuation characteristics of our thickness of our explosive charge and the density change at that detonation front.
And there's Lee Grossman also had a paper in '89, which basically said mu L equals to 2, which is like 13-14% transmission, so it's very similar. Any other questions in the audience? Online? I have a question. Can you go to the 31 images that were acquired?
I really like that data set.
So when you look at this, it's sort of like fading. Is each one, are you just taking an image after an image after an image, or are you recording multiple images as the source is fading away? It looks like it's fading versus image 1, image 2, image 3.
So
What's
this,
that fading that I'm seeing?
yeah, so this is the GIF is just produced by taking these 31 individual images. So each is taken with one flash.
Yeah.
And then we just stack those images together with a very short time delay between them for the sake of the
Oh,
video.
and you're looping. So
Yes.
Oh, so, okay, so then the last one is almost, so you're saying frame 31 is almost black?
Yes.
Okay. I guess doing that slower would be good to see it, but it's going very quickly.
Right.
Okay.
Right.
Okay, so it's basically dark
That's the full
image.
lifetime. Yeah.
Oh, cool, okay.
It's kind of eerie.
Cool. They said basically the last image is a dark image because the anode snapped. Okay. Thank you. If there's no more questions, I'll thank the speaker again. Let's see. So when you say, Finn, when you say swath, do you mean like a region of interest you're extracting out? So a 2D area from the image you're actually taking statistics from, a swath?
Yeah, so
'Cause
with the
it's-
step wedge, we just take like an average rectangle and just take sort of
Okay.
the average out of all of that rectangle. For a swath out, you're averaging across the short dimension of your rectangle. So you're kind of taking all those, it's like taking multiple line outs next to
Oh, okay, so you're integrating over, yeah,
Yes.
you're just basically getting more statistics by integrating over a line out, multiple line outs.
Yeah, but then with a curved interface, you lose the ability to do that effectively. You kind of change your step response, and it becomes harder to actually measure your interface. It'll turn into a big blur instead of just a sharp interface in your line out. So I want to compare those more effectively.
Okay. And then the other thing you said in there was, oh, there was a chat question, uh-oh. Oh, please repeat the question, so I think we did that, hopefully. When you say